Some of the most beautiful and honestly useful things we see every single day are governed by a hidden property of light. We're talking about a layer of physics that's constantly at play, creating these incredible effects right in front of our eyes. I mean, really think about it for a second. You put on a pair of polarized sunglasses, right? And that blinding, painful glare reflecting off a wet road or the surface of a lake, it just disappears. It's not just dimming the world, it's specifically targeting and erasing the glare. How on earth does it do that? And then you've got this beautiful mystery, the shimmering, almost magical colors on a peacock's feather. Well, they aren't made of pigment at all. There's no blue ink, no green dye. In fact, if you were to grind that feather up, you'd just get a boring brown dust. The color is a complete illusion, a trick of physics. So, what's the secret? Well, the answer to both of these puzzles, the sunglasses and the feather, is found when we realize that light is much, much weirder than we were taught in school. The idea that light travels in a simple straight line, that's really only half the story. So we've basically got two different ways to model light. There's the ray model, which is the one we're all familiar with. It says light travels in straight lines, and it works perfectly for explaining things like shadows or how a magnifying glass works. But for our mysteries, that model is useless. We need the wave model, which sees light for what it also is, a wave that spreads out. And if light is a wave, it has to act like one. One of the key behaviors of any wave is something called diffraction. Just picture dropping a pebble into a calm pond. You see the ripples spread out, right? Now, if those ripples hit a wall with a tiny little gap in it, they don't just go through in a straight line. No, they spread out all over again on the other side. That spreading is diffraction. Okay, so if light does this, why don't we see light beams bending around corners all the time? Well, it's because the wavelength of light is just unbelievably tiny. I mean, ridiculously small. For us to actually see this wave-like behavior, light has to pass through an opening that is almost as small as its own wavelength. But one experiment managed to prove it, and it changed everything. So, if this effect is pretty much invisible to us in our daily lives, how did anyone ever prove it was happening? It took one of the most brilliant and, frankly, elegant experiments in the entire history of physics to give us the proof we needed. So, let's go back to the early 1800s. A guy named Thomas Young sets up this really simple but genius experiment. He shines a light at a barrier that has two incredibly thin parallel slits cut into it, and he just looks to see what kind of pattern the light makes on a screen behind the barrier. Now, if light is just a stream of little particles, you'd expect to see two bright lines, right? One for each slit. Simple. But that is not what he saw. Not even close. Instead of two lines, the screen lit up with this bizarre pattern of many alternating bright and dark stripes. This result was an absolute bombshell, because there was only one way to explain it. That pattern is caused by something called interference. As the two little light waves spread out from the slits, they start to overlap and mess with each other. In some places, the peak of one wave meets the peak of another, and they team up to make a super bright spot. But in other places, the peak of one wave meets the valley of another, and they completely cancel each other out, leaving a spot of total darkness. That strange pattern of light and dark bands was the smoking gun. It was the definitive, undeniable proof that the simple ray model of light just wasn't the whole picture. Light had to be a wave. Okay, so now that we get the idea of interference, we can finally crack our first mystery, because it turns out a peacock's feather is using this exact same physics to create those incredible colors. So first, let's imagine taking Young's experiment and just cranking it up to 11. Instead of just two slits, what if you had a screen with thousands and thousands of them, all packed incredibly close together? That's called a diffraction grating. And what it does is amazing. It splits white light into a beautiful rainbow because each color, or wavelength, interferes at a slightly different angle. And here is the truly mind-blowing part. Nature figured this out a long time ago. A peacock feather, when you look at it under a microscope, is made of these tiny, perfectly parallel rods. They act exactly like a diffraction grating. The only real difference is that light reflects off of them instead of passing through them. So when white light from the sun hits the feather, this microscopic structure causes the different colors to bounce off and interfere with each other. Some colors get canceled out completely, destructive interference, while other colors get amplified and become super vibrant.
And the colors you see change depending on the angle you're looking from. It's not pigment, it's physics. It's structural color. Absolutely amazing.
All right, so interference explains the peacock, one mystery down, but it has nothing to do with our sunglasses. To solve that one, we need to dive into another hidden property of light waves, one that's all about direction. And this property is called polarization. Now, the technical definition sounds a little scary, but the idea itself is actually pretty simple. Just picture a light wave as a wiggling rope that's moving forward. Polarization is just the direction of that wiggle. Is it wiggling up and down, side to side, or at an angle? That's it. That's polarization. So light from the sun or a lamp is what we call unpolarized. It's a total jumble of waves wiggling in every random direction at once. A polarizing filter then acts kind of like a picket fence or a vertical gate. It only lets the light waves that are wiggling up and down get through, and it blocks all the others. Now this is where it gets really cool. What happens if you use two filters? So you pass light through the first vertical filter. Now all the light that gets through is wiggling vertically. If you then try to pass that light through a second filter that's turned sideways, a horizontal gate, what do you think happens? Nothing. The up and down wiggles can't get through the side-to-side gate. All the light is blocked. Okay, and here is the final piece of the sunglasses puzzle. It turns out when light reflects off a flat, horizontal surface, like a road or the top of a lake, that reflected light, that annoying glare, becomes strongly horizontally polarized. Its wiggles are almost all side to side. And there it is. Polarized sunglasses are just vertical polarizing filters. They're a vertical gate that almost perfectly blocks the horizontal wiggles of the glare, while still letting in plenty of the other useful, unpolarized light from the world around you. It's so simple, and yet so incredibly brilliant. So, there we have it. From the shimmer of a peacock's feather to the glare-cutting power of sunglasses, it all comes down to the weird and wonderful physics of light as a wave. It's all around us. But just when physicists thought they had light all figured out, the story took an even stranger turn. We started with that super simple ray model. Then we graduated to the wave model, which explained everything for us today. But in the 20th century, scientists discovered that on the tiny quantum level, light also acts like a particle, a little packet of energy called a photon. And this leaves us with a really deep and fascinating question. We have seen the absolute rock-solid proof that light is a wave. And yet, there's just as much solid proof that it's a particle. So which is it? How can it possibly be both things at the exact same time? And that, right there, is one of the biggest mysteries at the very heart of modern physics.